Where'd you get the that? Yeah, I ended the class. Yeah, I know. I ended the class like at 78.9. Yeah. I thought it was crazy. I thought, yeah, that was the end of the issue. Yeah, I didn't even try on final. I literally like wrote a bunch of stuff into it. Yeah, you're taking it to my Yeah, I mean, like, you do that. Oh, you did. What did you get? Are you gonna read the AG? Yeah,
I'll be right back. Maybe go to charger.
did you guys have the same grade?
Yes, sir.
How many people registered for the class?
You? It's like 25.
We're having a hard time getting.
Well, I emailed him, he said we don't need to come like in person, keep trackers,
That's what he's trying to do right now, right?
yeah. I mean, you
You're
don't
gonna
have to,
switch to this?
oh, no, like, you don't have to attend, you can join through Zoom, but you have to come in person. Yeah, so I refund myself.
Except for the exam, which is like every other week.
It's like next Thursday, and then another 2 weeks, and then we have final.
Yes. What? Oh, that's you. That is the first grade. You gave me a 30 on the test. Wonder how it happened to Danny. Oh, that's. I was some class. Right over here.
Yeah.
If I get extra time, it took me a while. Dang. You guys are out of it pretty quick? Guess so?
Yeah. Yeah. This should do that. I have 100%. But,
Yes, just in case I do run out of think of it.
yeah. So wait, what are you taking overtime or this class?
Yeah.
Oh, are you gonna come in person? Like, yeah. About 40 minutes.
Yeah, it makes sense for you. And then it was like 12 minutes.
Oh, really? You live around here?
Straight up to the cabin, so straight down to the traffic. Probably went home there.
Yeah. For next semester, are you taking that Monday, Wednesday class, the 322 hour?
The one at night?
Yeah. Yeah, I wasn't in class at like 12 and I have a 7 hour gap. So I drive 40 minutes home.
You go home?
Yeah, well, what am I gonna do for 7 hours?
Every
Fuck yeah.
Tuesday, I was born.
Like 7 hours is crazy.
I wish we could take that somewhere else.
I know, it's such a 7 is ridiculous. But yeah, I'm just gonna drive home and come back.
I did 2,500 today. Really? Just free stuff? Yeah, we just make stuff like the paddles, the things. You write that? Yeah, I write that.
What?
I don't even want to go home. I'm supposed to.
I don't take it.
I should tell them that they don't have any classes here in bed.
I am, I used to, well, I have like a kitten in the teenager. That's one of my effective. That's how you feel. So when there's some planning, it's very like real big, and there's guys that still have three the little things around going, looking up reality. It's more complicated. But they're both played by right. You know the fertility license? Yeah, but I company. Yeah, they have their around and they're moving because of the Olympics. Because of the closer. So they're clearing out the warehouse. And they're bringing last Friday. A bunch of stuff, like stuff for moving. My oh free. No way. They do not do it $1,000. You think I should go back? Is it still available? I want to go back. So if she sends me some stuff, I can come back in. I'm going to try to get it in. And it's crazy. Dude, I went through rooms. What? I have like unreleased stuff. Or stuff that has to be out. Something? Or possible? I just log in to figure out. I was like, what size are you? 34. Like a lot of movie guys are only 32. And I was like, 30, depending on like 60. So the business was getting. Oh, I mean, I'm like, because like, I think you don't say it. But the word, for someone, I only work here. Even like, if I'm taking food, that's my work. Yeah. Probably, I wanted to change the group. Basically, we want to be able to, really kind of, at least, because I think it's I took the whole day yesterday to get here and reading too. Yeah, like I do it for work. Yeah, so that's what he, when she got to, when she did drawing, and she did so fast. It's so yeah, because she did it at the beginning, she's like, oh, I'll just write, and I was like, no, I need to do it.
All right, it's 3 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good. Good to see everybody. Welcome to the summer sessions. This is summer session A at Cal State Fullerton. This is EGME 333 Fluid Mechanics. If you have not seen on the screen already. So my name is Professor Justin Tran. I will be your instructor for the next 5 weeks. Hopefully everyone got my email. I think everyone that's in the class should be on the Canvas, and so hopefully everyone had a chance to at least get my email. And if you hadn't had a chance to look at the course website or the syllabus, we'll go over that today. But yeah, today is the first lecture. So I guess before we begin, this is my first time teaching summer. It's a 3-hour class. 3 hours is a very long time. So just to be talking up here, so I'll probably take a break halfway through. That's probably what I intend to do for the rest of the whole summer session. So we'll probably go for about an hour and a half. We'll take a break and then we'll do the second hour and a half after that. Okay. But yeah, so today the plan is to, for the first half of the class today, just kind of introduce the class in terms of what to expect, in terms of, what fluids is, what to expect for the summer session. We'll go over the syllabus, we'll go over the course website, then we'll take a break, and we'll come back, and we'll have kind of our first kind of real lecture after that. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay, so a little bit about myself. So my name is Professor Justin Tran. So my office is not in this building; it's in the other building. It's in engineering. If you want to contact me, I definitely prefer email. Although technically my office number is on the syllabus, but I vastly prefer email. So my email address is justran@fullerton.edu. I always tell people it kind of looks like I stole that email address from a running club here at Cal State Fullerton, but that's just my name. That's just kind of how it is. I grew up here, so I grew up in Cypress, California. If you're not sure where that is, that's just, maybe 10 miles west here on the 91. So this is very much home to me. I just saw my parents this morning. Actually, I dropped my son off to at my parents' place. So very happy to be here. Very happy to be teaching here. And in case you were curious, my research interests are actually very closely aligned with fluids. So even though I haven't taught this class for 5 years now, but I've always considered myself a fluids guy. So my research interests are in engineering applications to heart and blood disease. And of course, I'm interested in, just as an educator in STEM, just how we can kind of better do this educating stuff. Okay. All right. So next thing I want to introduce here are the learning objectives. And so I think probably for a lot of you, this will be your first time having me as an instructor. So at the beginning of every class, you will see me post what I call the learning objectives for the day. So just at face value, you can think of these as kind of, just like an outline in terms of what we are expected to do for that day. So I always recommend people just to write these down at the top of your notes, just for the case of, on the one hand, it helps organize your notes. And so, it just kind of tells you at the top what these sets of notes are. But it's also kind of a way to kind of tell you what to expect in the class because, I'm going to have these learning objectives, and then as we go through the lectures, we'll be covering each of those learning objectives. And so you can kind of, think of it almost like a checkbox in terms of, what we cover for that day. Okay. And if you actually look carefully at these too, I'm very intentional in terms of how I word these learning objectives. And so you should see that every one of these objectives here starts with a verb. So describe what a fluid is, or list the applications of fluid mechanics. Because all of these I write my learning objectives in a way such that you can basically they're kind of self-contained in terms of what you can do to demonstrate that what that learning objective is telling you what to do, right? And so instead of just saying we're going to talk about what the definition of a fluid is, right? By the end of class today, you should be able to describe to me what a fluid is, right? And so they're kind of questions in of themselves, right? And one thing I always like to do, I always like to take learning objectives and actually put them as questions on the exam. So I would definitely pay attention to them, okay? So I write them down at the beginning of class. I usually come here, or I usually try to come here 10, 15 minutes early. So definitely write these down and definitely use them to help you with these stuff. Okay. Okay. All right. So let's get to introducing the class. So fluid mechanics, I think, has a reputation. Usually not a very good reputation, and wherever you go, it's not just here. So it's not just me that's an asshole. Every fluids instructor everywhere is an asshole. So fluids is going to be a hard class, right? So let's talk about what is a fluid. Okay. So if you go to Wikipedia, they will tell you the definition for a fluid. This is a very scientific definition. So fluid is any substance that continuously deforms when under an applied shear stress or external force. Okay. Now this is correct, right? And I presented it to you because it's correct. But it's not the most useful, right? And so I always like to actually go back to my 8th grade science course to define what a fluid is. And so a fluid is any kind of substance that assumes the shape or part of the container that's in, and it flows easily, right? And I've underlined the word flow there because that's really kind of what fluid mechanics is all about, and what separates fluids from a solid. In that when you apply a force to it, it's going to flow, right? So you pour water out of a water bottle, that water is going to flow outwards, right? You see water that's crashing on the beach, waves, that water is flowing, right? It's continuously deforming, okay? And to put it in terms of, molecularly what's going on, the particles are moving and sliding past one another in a fluid, which doesn't happen in a solid, right? In a solid, all the molecules, all the particles are really closely packed. They don't really move past each other unless you intentionally break the solid. But in a fluid, that can very easily happen. Okay, so let's talk about some applications, right? And so, I think probably the most obvious application for fluid mechanics, especially in the realm of mechanical and aerospace engineering, is in, well, aerospace engineering, right? And so if you're going to get into, design of airplanes, designs of rocket ships, these devices and these vehicles, they work based on our knowledge of fluid mechanics, right? So everything that we know about lift, everything that we know about drag, it all is based very heavily within fluid mechanics. Right? And so if you aspire to work for one of these aerospace companies, fluids is something that you're going to have to be really good at because that's going to be part of your everyday work. Okay? There's also a lot of applications in public works, right? And so what you're seeing here is a picture of the California aqueduct, right? And so based on large bodies of water that's moving through, right? Water is, I think water is probably the first fluid that people think of. Water is part of our everyday life. We have to drink water to survive, right? And so moving water to those locations, to people's homes, to the businesses, that's a big part of fluid mechanics as well. Okay. And even on the microscopic level as well, right? So what's interesting about fluids is that there's applications where, you have these very large aqueducts, very large structures, but also fluids is very relevant for the tiniest of structures as well, right? So what you're looking at here, this is actually a picture from my own research. So this is a simulation of blood flow in a person's arteries. And so an artery is usually no bigger in diameter than a centimeter usually, right? So you're going by something that has a diameter of several meters down to something that has a diameter of a centimeter or two. Okay. Right. So there's lots of applications for fluids, right? And what I hope from this class, and I know this class is very, very fast, but what I hope is that you'll be able to see, at least in your daily life, just how important fluids are to kind of all the things that we do on a daily basis. And you can start to apply some of the knowledge that we learn to understand how some of these devices or some of these phenomena work. Okay. All right. Any questions on this so far? All right. So by the way, I try to pause for questions as much as I can, but don't be afraid to raise your hand at any point. Okay. So I am looking out, and I am checking the Zoom as well. And so if you have questions, just raise your hand or put something in the chat, and I'll answer. Okay. Okay, now let's talk about fluid properties. And so we'll go through this, more in detail in the second half of the lecture today. Again, I kind of designed this class with the usual semester in mind. So usually these slides are just the one thing I do today. But then, just because this lecture is kind of two in one, we'll go over the second part here. Okay. But one thing I think is really, I think harder to grasp for people in fluids is that, when we talk about properties of fluids, we're not talking about extensive properties. Okay. So when you talk about solids, a lot of times you talk about extensive properties, so things like volume, things like mass. Okay. The thing with fluids is because they're constantly deforming and because they're constantly flowing, they're constantly changing shape, a lot of times it doesn't really make sense to use these extensive properties. And what I mean by extensive properties is that, the value of an extensive property depends on the amount of substance that you have, right? So the more stuff you have, you're going to have a higher volume. The more substance you have, the higher mass it's going to be. Okay. Intensive properties, on the other hand, are not dependent on the amount of substance. There's something that's intrinsically defined by that material or that fluid on its own, right? So things like density, right? So density probably is a concept you're familiar with. Density is the mass per unit volume, right? So it doesn't matter how much water, whether you have just a bottle of water or you have a whole swimming pool of water, right? That water is going to have the same density, no matter how much substance there is, okay? And when we talk about fluids, we're always talking about these intensive properties just because of the nature of how fluid can flow. Okay. Okay, so let's talk density first. So density is the way that we characterize the mass of a fluid. Okay, and it's given the symbol rho. So the rho, if you've never seen that symbol before, it's like a P that kind of is leaning slightly to the right, but it's a Greek symbol called rho. Okay, and like I mentioned, density is defined as the mass per unit volume. So some common units for this would be kilograms per meter cubed. That's the standard SI unit for density, or grams per centimeter cubed as well, right? So what matters is that you have a mass divided by a volume, okay? So fluids with higher density will be heavier than fluids with lower density, okay? And differences in density will cause things to float, right? So buoyancy is something that we're going to talk about, probably not tomorrow, but probably on Thursday of this week, okay? And what's interesting about density is that it also changes with temperature as well, right? So if you've ever seen a hot air balloon, the way that works is by playing on this idea that if you heat up a fluid, then its density actually goes down. It actually disperses the particles. It makes it actually lighter than the fluid surrounding. Okay. Okay. So here I have, the video might actually work, but I'm actually not going to play the video. I think just this image, I think, is enough here. So, you can do some really interesting things with fluids because, if you put two fluids together and they have different densities, and assuming that they don't mix, right? The heavier or the more dense fluid will actually fall to the bottom. So you actually get kind of really interesting phenomenon like this, where you have, a very dense fluid here at the bottom, a less dense fluid on top of that, and then, the lightest fluid on top of that, and you can add different colors here to make it kind of separate, okay? And even, right, you can even put in objects there as well, because the laws of density also and buoyancy also apply to solids as well, right? So you get this kind of really interesting kind of phenomenon like this, where you have kind of, solid objects that are seemingly kind of suspended or floating in this fluid, all just because of the density that they have. Okay, so another way to kind of express density is through this idea of specific weight or specific gravity. Okay, so these are often terms that we'll go over as well, especially when we go over the concept of buoyancy. Okay, so the first thing is specific weight. So specific weight has the symbol gamma. It kind of looks like a Y that kind of at the bottom part kind of twisted up on each other. Okay. So specific weight is just the density of the fluid multiplied by gravity. And so the units for specific weight, unfortunately, I don't have it here. Units for specific weight is a force per volume, right? And so, basically taking a mass and converting it to a force by multiplying it by gravity. Okay. And then another kind of offshoot of that is called specific gravity, which is the density of the fluid divided by the density of water. Okay, so specific gravity is a very kind of niche kind of metric or very niche property. A lot of times you don't use it, but it is very useful to know if an object will float in water, which has a lot of applications. Okay, because one thing that you'll see, or one thing that you'll learn when we get to buoyancy, if a fluid or if an object is less dense than water, if its density is less than water, it's going to float in the water, right? So specific gravity is just a very quick way to determine, whether an object will float or not, right? So if you have a specific gravity that's greater than 1, then the object will sink. If you have a specific gravity that's less than 1, it's going to float, because it's just specific gravity is the ratio of those things. Okay. All right, so we'll go over this in more detail. Again, I kind of designed these slides to be kind of a one-day thing, but we are actually going to do a lecture after this, folks. So we'll go over this in more detail later. But I did want to kind of introduce this idea. Okay. Okay. Any questions on density or specific weight, specific gravity? Okay. Good. Okay. Next, we have viscosity. So viscosity is another property of the fluid. Viscosity is something that we probably won't talk about until maybe the second half of the session, because viscosity does get quite a bit complicated. But viscosity is a property that describes how easily or how difficult it is for a fluid to flow, right? So I think all of us, we have this kind of intuitive kind of understanding of viscosity, right? So if you've ever tried to take honey from the little squirt bottle from the market and try to squeeze it out, you have to have the patience of a sitting monk sometimes to get it into your drink, right? Whereas if you were to pour out a bottle of water, it happens very quickly, right? And the reason for that is because of the difference in density, right? So fluids with higher viscosity tend to feel thicker or feel stickier, right? Because they just don't flow as easily. Okay. So just as an example, right? Think of the sensation of if you were to take your fingers and plunge it into a pool of water versus plunging into a pool of honey, right? And so that's going to have a very different sensation because of their difference in density. Okay. One easy way to kind of think about this is that the higher the viscosity of a fluid, the closer it is to actually behaving like a solid, right? And so there's actually a huge field of research on this called viscoelasticity, because there are a lot of substances that kind of exist kind of in the area in between a solid and a fluid, just because their viscosity is just so high. Okay. Okay, and then you can also do, this video might work too, right? So kind of the classical kind of test for viscosity is, taking an object and dropping it into a pool of fluid, right? And depending on how quickly the object kind of falls to the bottom, that will tell you how viscous that fluid is, right? And so, we can try to see if this video will work. Oh, it works. For some reason, it was not working on my laptop at home, right? So you can see, depending on the viscosity, so they're taking basically just a marble and just dropping it into that into a cylinder, right? And so they have 5 different fluids here. They have vegetable oil, they have motor oil, they have dish soap, they have maple syrup, and they have honey. Honey is kind of the classical high viscosity fluid. Okay. I should have drank some water before this, so I will take a break and let you guys watch the video. So you can see that, as he's dropping the marbles in the different fluids, it's taking longer for certain fluids just because of how viscous they are, right? All right, then we got the point. Oops. Okay. All right, and so viscosity, there are a couple ways for us to measure it, right? And so there's a measure called dynamic viscosity, and so dynamic viscosity has units of Pascal seconds or kilograms per meter second, right? And so that's the symbol for dynamic viscosity is this kind of fancy looking U here, which we call mu, right? Not to be confused with Pokemon, but that's just the Greek symbol mu, okay? And the other form of viscosity is what we call kinematic viscosity, which has this symbol nu, right? And so it's a kind of like a fancy looking V, okay? Now the difference between the two is just whether or not you're going to divide by density, right? So the relationship is that kinematic viscosity is equal to dynamic viscosity divided by the density, okay? And then which one you use, they're both valid, right? It really just kind of depends on the application or the types of equations that you're using, okay? But don't be confused about the different viscosities, or I guess, when you're looking up fluid properties, just kind of be aware of which one that you're looking up based on the units that you're using, right? And then don't plug in the wrong one in the wrong equation. Okay, all right, any questions on viscosity? Okay, good. Okay, all right, so that's just a very, very brief introduction to fluid. We'll kind of talk more about this after the break as well. But before we start talking about the syllabus, before we start talking about kind of the logistical things of the course, let's kind of just take a moment to describe or talk about why fluid mechanics is important. Okay. So like I mentioned at the beginning of lecture today, fluids form a very core part of many, many engineering systems. So airplanes, probably the first thing people think of. Engines, if you're going to work on powertrain, on automotive, then this is something that you're going to have to know. Water pipes, medical devices, so on and so forth. Okay. So if you aspire to work with any kinds of these devices, which, if you're going to be a mechanical engineer, you can't really get away from it. So most systems that you're going to work on as a mechanical engineer are going to have to deal with fluids in some way or shape or form. Okay. And, the thing with fluids is that, it's the reputation for fluids being difficult is like I said, not just here. It's difficult everywhere. And so, if you have a strong, understanding of fluids, you really understand it really well, then, it's going to be valuable knowledge that you're going to see not that many people have. And so, if you want to work on designing these systems or improving these systems or kind of discovering new advancements in these fields, then you're going to need to have a strong background in fluids in order to achieve that. Okay. All right, so let's go over just an overview of the course, right? And then we'll go over the syllabus. So, I have kind of this this chart here, right? So in the middle here, we have fluid mechanics. That's just kind of the central theme for the entire course, right? And then we're going to break this up into, I would say 4 different quadrants, right? We're going to start on the left. And so we're going to start on fluid statics and talk about fluid properties. And then we're going to work our way over to the rest, okay? I will say the majority of the course will be in this right quadrant right here, fluid dynamics, which is the science of fluids in motion, right? Because that's kind of where a lot of the theory is, and a lot of the difficulty is, but we'll work our way up there, okay? And you can expand this even further into all the different types of subtopics that we're going to go over as well, okay? Now, I showed this to you, not to intimidate you and not to make you write this down now. it is a lot of stuff, right? So part of the difficulty of fluids is that there's just a lot for us to cover. And honestly, if you ask me, I think this session is not long enough to cover everything that we need to. But my hope is that by the end of the summer session, you'll be able to look at this chart right here and say, hey, we've learned a lot of stuff. We understand a lot about fluid mechanics. Okay. Okay. And so with that, let's go over the syllabus. And so, I think I sent everyone the syllabus. I know a few people have taken a look already because I know there's a few questions. So hopefully we can answer those questions about the syllabus today. Okay. Okay. All right. So let's talk office hours first, right? So my office, like I mentioned before, is an E220. So that's on the second floor of engineering. That's the building on that side. Okay. But I also offer office hours over Zoom as well. Okay. So office hours are basically very simple for this class. It's basically just an hour before the lectures. It's from 1:30 to 2:30 on Tuesday, Wednesday, and Thursday, right? So if you have questions on the homework, if you have questions on the lectures or anything, just come by to my office early or hop on the Zoom call early, and we can talk about it during those times, okay? So office hours, are mostly for discussing any points of confusion about the course, any homework questions, questions about the exams, or just stop by and say hi. That's fine too. Usually I'm just kind of today I was just kind of sitting in my office, twiddling my thumbs whether someone's going to come or not. But usually people don't come per se. And that reminds me as well. So I know it looks like I think everyone's here today. But if you've been to the Canvas site, you'll notice that there is a Zoom link for the lecture as well. So I am streaming the lectures. In fact, I'm streaming it right now. I'm recording all the lectures as well. So you're free to attend the lectures over Zoom if you want, right? And I know it's not always the easiest to kind of get out here to Fullerton. I do require that you are in class on the days that we do exams, but every other day you are free to attend the lectures over Zoom. And of course, the recordings will also be there for your references as well, okay? I don't recommend watching the lectures, even though the recordings will be there on YouTube. I don't recommend waiting until right before the exam to watch all the lectures. I know that's some people do that. And I do optimize my voice, so 1x speed is the perfect kind of speed to view the lectures at. So don't view the lectures at 1.5x speed. And don't think that you're going to sit on the weekend and watch 9 hours of fluid mechanics lectures. Don't kid yourself. That's no one wants to do that. So the best way to kind of experience this class is to kind of attend the class when it's scheduled 3 hours, Tuesday, Wednesday, Thursday. Even then it's going to be really fast, but try not to fall behind. That's kind of my recommendation. Okay. All right. Next, we have the course level learning objectives, and so these are learning objectives that are guiding kind of the entire organization of the course itself. Okay. So every day, every lecture will have our learning objectives for that particular day, for that particular lecture. But I also have learning objectives for the entire course as well. Do you have a question? Oh. So these learning objectives will be covered throughout the entire summer session. Okay. Now these are a lot more broad, as you can see, and probably a lot of them don't make sense right now just because today is the first day of class. But hopefully again by the end of class we'll be able to look at these objectives and say that hey I can do all of these things. Okay. This is also just to show you that I am organizing this class. I'm not just coming up here and just saying whatever I want each day. So there is some degree of organization, and it's organized by these subjects. Okay, let's talk deliverables. So of course this session is short, right? It's only 5 weeks, and basically you can assume that there's going to be a homework assignment due every single week. Okay. Now the due date for the homework assignment is going to change depending on whether there's an exam that week or not. This week the homework is due on Friday, but the next week you're going to see the homework is due on Wednesday because we have the exam next Thursday. Okay. But next week's homework assignment will be shorter than this one. This one's a little bit longer. That's why I give you the okay. So besides the homework, there's going to be 2 midterm exams and 1 final exam. Okay. And the dates for all the exams are shown at the bottom of the screen. Okay. So the first midterm is going to be next Thursday, June 4th. And so that's going to be 80 minutes. It's not going to take the whole lecture. And right. So my plan is to give the midterm for the first half. We'll take a break and then we'll do the lecture for the second half. Midterm 2 is going to be 2 weeks after that, Thursday, June 18th. And then the final exam is going to be the week after that. There's not much for us to cover after the second midterm, but there is a bit of stuff. And the final exam is going to be for the entire class session, 107. Okay. No makeups are planned, so please, if you cannot make one of these exam dates, please let me know as soon as possible. I am flexible, so there are ways that I can give you the exam if you can't make it to the exam dates, but just you have to let me know kind of as soon as possible so we can arrange that. Okay. Midterms will not be cumulative, so midterm 2 will not include the stuff from midterm 1, but the final exam will be. Okay. Now let's talk the course grade breakdown. Okay, so I think I have a pretty standard breakdown in terms of the letter grades, and so if you have a 90% and above, that's an A. 80% above, that's a B, or minus and plus accordingly. But one thing I do that's a bit unique is that I do count the different exams differently depending on how you do. Okay, so if you look at the first part of this slide here, you can see homeworks are worth 10% of your grade. Final exams are worth 40%. Now, the two midterms, one of them is going to be worth 30% of your grade. The other midterm exam is going to be worth 20% of your grade. Okay? Now, the way I determine that is just whichever midterm you score higher in, I'm going to count that for a higher percentage of your grade. So let's say you do midterm 1, you do really well. So let's say you get like a 90% on midterm 1, right? I always kind of say that's like money in the bank, right? So that's you can say that's 30% of your grade kind of locked in. But let's say that you take midterm 1, let's say that you didn't do as well as you want. You can kind of make it up for it on the second exam, because let's say you do really well on the second exam, then that's going to count for a higher percentage of your grade. Okay. So I do this automatically, right? And so just whichever midterm. So of course, most ideal thing is to do well in both exams, but if you don't do well on one exam, there's a way for it to kind of buffer in your grade this way. Okay. Okay. Last thing I'll mention as well. So final course grades, they may be scaled in the student's favor. So what that means that after everything is in, so final exam, midterm exam, homework grades are in, what I always do is that I compute the overall class average in terms of percentages, right? And if that percentage is lower than kind of the typical average for this class, usually I like the average for this class to be around, maybe 78, 79%. Then what I'll do is I'll add points to everyone's grade until that average meets that threshold. And so let's say that, after everything's in, the overall class average was 71, 72%. I'll probably add, 6, 7 points to everyone's grade in order to reach that 78, 79%. Okay. But I don't know what that scaling is going to be until the end of the session, right? And so, I don't curve individual exams, but I do kind of curve at the end, although it's not a strict curve in a way. It's just I just add points to everyone. Okay. All right. Any questions on deliverables or grading policy? Okay. Okay. Textbook. So there is one textbook for this class. It is the very classical fluid mechanics textbook. It's the Munson Young and Okishi textbook. I think I have the version from 2000. The one I have in my office from like 2000, like 2010, because that's when I took fluid mechanics. Way long ago. So it is required. It is a great textbook. But I always tell people, don't pay full price for a textbook. The textbook publishers are not paying me to be here. They provide they're a necessary evil, I would say, right? So if you can find a cheaper version of the textbook, maybe an older version that's used on Amazon, or maybe you just happen to be, sailing the high seas online and you happen to notice a PDF of the textbook, that's I always recommend that as well. So don't pay full price, but this textbook is good, so I do recommend it. I'm not going to be assigning any problems out of it, so I will be writing all my own problems, but it is useful to have as a reference, right? Because during the lecture, there's only so much I can cover, and so there's going to be derivations, there's going to be examples that I skip that you'll see more in the book, right? So people always ask me, if they want to see more examples. There's a lot more in the textbook for you to do. Okay. And this textbook is very good. They actually, go through all the steps pretty good detail, right? And so they'll give you a lot of really good information. Okay. All right, course website, Canvas. So we'll be taking a tour of the Canvas site after we're done with these lecture slides. But just know that, everything that I produce for the class will be posted onto Canvas. So all of the lecture notes, all the lecture slides, all the homework assignments, homework solutions, exam solutions, study guides, any handouts, there's a couple handouts I have for this class, any additional examples, they'll all be posted on Canvas. And so, you should definitely be familiar with Canvas, get used to going there for the content. All the lecture recordings will be there as well, right? It kind of helps to kind of check the Canvas on a regular basis, okay? Announcements will also be made in Canvas, right? And so I do use the announcement system on Canvas. Let's hope that Canvas isn't hacked again over the summer, so I can access that. But every announcement that I make on Canvas will be directly emailed to you as well, okay? And like I mentioned, the Zoom links, if you want to attend the lecture over Zoom, they're accessible on Canvas, as well as the Zoom link for office hours as well, okay? But again, we'll be taking a tour of Canvas right after this. Okay, course policies, and so homeworks. So I do accept late homeworks, but just with how quickly the summer session is going to go, I highly recommend that you stay on top of the homeworks. But I do recognize that it helps to have a late policy. Okay, so I do accept late homework, and they will be docked 10% each day that it's late. And if for some reason you cannot upload it onto Canvas, you can always scan and email it to me as well. Okay. Regrades. And so, if you want me to take a look at your exam again, you think that you deserve more points, I'm always happy to take a look. Please, email it to me. But I only accept regrade requests up to a week after I return that whatever it was to you. Okay. So what you're going to notice is that, maybe not so much on the homeworks, just because there's the homework's going to go very quickly, but at least on the exams, I do leave feedback, I do leave comments. And so I do want you to read those comments and feedback, just because they're going to be important for the final exam. So this is kind of my way to kind of encourage you, so that you don't just look at your score and throw it away, and then realize at the end of the semester, like, oh, I need 5 more points. Let me check that. So please look at the comments kind of early, just so that you can read that feedback. Okay. Emails. So it's a little bit different this summer. This is the only class I'm teaching for this session, but I am still receiving other emails for, like, my research and my grad students and things like that. So if you do have a question about the class, please include EGME 333 in the subject line. That way I know it's someone from this class. Okay. And usually I'm pretty good with emails. I do try to respond basically as soon as I see them. Sometimes I'm just on my computer and I can respond to you within 5 minutes, but at the latest, 2 business days afterwards, I'll get back to you. Okay? If you email me at 11 o'clock at night, I'll probably email you back the next morning. Okay, last slide here before we take a tour of the Canvas website, academic dishonesty. Okay. So I have a strict policy on academic dishonesty. So this will not be tolerated in this course. It's a little bit less of an issue in this course, because this course is very exam heavy. So unless you have the ChatGPT chip in your brain, you only can really access it on the homeworks. But even on the homeworks, as easy as it is and as convenient as it is, I do recommend that you do it yourself, or I do require that you do it yourself. Okay. Because one thing I'll say about this class, a little contradictory to kind of what I said earlier, that this class is easy. And it's not easy in the sense that, everyone is going to get an A. It's easy in the sense that, the problems that we're going to be doing in this class, the problems that you're going to be doing on the homeworks, I'm pretty confident that if you just throw those into ChatGPT, you throw those into Claude, they can give you a fairly competent answer. Maybe not a very good answer, but something that's competent. Okay. So it's easy in the sense that an AI could probably do every single problem in this class, right? But that's not the point of taking a class like this, right? So you don't pay money to take a class with Gordon Ramsay just to send your cousin to take the class for you, right? The point of the class is to gain the knowledge and skills that you're going to apply later on, right? Because after you graduate from here, you're working at places like Boeing, you're working at places like SpaceX, Northrop, Toyota, all these automotive companies, right? They're not going to be asking you to do problems like the ones that we're doing in this class, right? They're going to be asking you to do problems that are more advanced, that require more advanced knowledge than what we're going to cover, right? But to get to that advanced knowledge, you have to kind of build your foundation. And kind of the unfortunate thing is that the foundational skills, foundational questions, and foundational knowledge, that's something that's easily accessible through a tool like ChatGPT or Claude. Okay. So I do ask you guys that, if you're struggling with the homeworks, if you think that you're having a hard time keeping up, especially in the summer session, because it is going to go very fast, please don't resort to that stuff. I'm like I said, you guys are the only class I'm teaching this summer. Please reach out to me as soon as possible. I promise you, I'll do everything I can to help you. If the office hours don't work out for you, we can schedule a time for us to meet outside. We can go over the homework and kind of go over step by step, everything that you need to kind of succeed in this class. Please just give me a chance. Because once you kind of start getting into what I've kind of noticed over the last couple of semesters, that once you start getting ChatGPT to do your homework for you, it gets even more difficult to kind of catch up later, right? Because I kind of see that kind of pattern where I'm really busy right now. Let me just do this really quickly just to get it in. But then when the exam comes, then you're screwed just because you haven't built up that knowledge. Okay. So please, reach out to me. I promise I'll help you. I promise I won't judge you. That's not my role here. My role here is to help you guys succeed and learn as much about fluid mechanics as you can. Okay. Okay. All right. So so one more slide. I apologize. So the very first homework, although this doesn't count towards the 5, that's why I call it homework 0, is introductions. We're only going to be spending 5 weeks together, so it is going to be very short. But it's going to be very intensive 5 weeks. So we're going to be spending 9 hours a week together. And so I would like to get to know a lot of you. And granted, I've already met a lot of you just through advising. But getting to know me in advising versus taking classes, it's different, right? So I would like everyone to send me an email, just introduce yourself, and you're going to get full credit just by completing it, right? So you can just send me an email that says, hey, my name is this. I'm not interested in getting to know you. Please just give me credit. I'm like, all right, that's cool. You have credit. But of course, the more you write, the nicer it is. I'll share things about myself too. Whatever you want to hear. I have a son. He just turned 10 months just last week actually. I have 2 cats. I love cooking. And so if you tell me about your hobbies, I'll probably share information about my hobbies, about my personal life, probably more than I should. I've given people pictures of my cats. I probably won't give you pictures of my son because that's my wife doesn't want that. Try to be open. Right? I think it's kind of nicer for everyone, right? And so I have these 4 questions here. You don't have to answer these, and so it's not an interview. I'm not interviewing you guys, and I'm not interrogating you. But if you're having a hard time getting started in terms of what to talk about yourself, you can think about these 4 questions to answer. But again, you can kind of just talk about whatever. Okay. So the due date for this is going to be this Friday. So it's going to be the same due date as homework 1, 11:59 by this Friday, May 29th. Please just send me an email, and then I will give everyone full credit if you send me this. Or I'll give each person that send me full credit. Okay. All right. Any questions on syllabus before we get to the Canvas site? Yes.
Or are you okay with the Canvas?
I would prefer email, just so it's all kind of in one place. The Canvas thing, I have to kind of go to the Canvas website. So it's not, I won't penalize you for the Canvas stuff, but I do prefer email. Yeah. Okay. All right. So let's go through, let's go ahead and switch gears. Let's go ahead and go through the Canvas site, and then we'll take a break. Okay. Okay. Okay, so this is the Canvas site. So hopefully everyone has access to it. In fact, let me go ahead and click on this so you can see what it would look like as a student. Okay. Oh, this is new. I have the announcements here. Okay. Okay, so if you go to the Canvas website, this is what you should see. Okay, so I try to keep it fairly clean. So I disable a lot of the weird apps and stuff that they have on Canvas. So I try to keep things just to the absolute basics. Okay. So the first page you're going to come to on the Canvas site, this is the home page. So you can see this is the name of the course here. There's me. There's my email address in case you forgot. These are the class times. So we're meeting every Tuesday, Wednesday, Thursday, 3 to 5:50 p.m. Okay. Location is in CS 304, which all of you are aware of that because you are all here. But you can also attend on Zoom as well. Okay. Here we have a description of the course. This is just straight from the syllabus. We have the course learning objectives. You can download the syllabus here as well, right? So if you click on this, you'll have the PDF version of kind of what we just talked about. And we have our Zoom links, right? So you can have, we have our Zoom link for attending the lecture, and the Zoom link for attending office hours. Okay. Okay. Now, the most important part of the home page here is what's at the bottom of the page, which is our course outline. Okay. So you can see I've broken up this entire summer session day by day, actually. And so in terms of, exactly what we're going to cover each day. Okay. So we're here right now. So this is week 1, part 1. So we're going over course introduction and fluid properties. Okay. And so what's going to happen as we go through the summer session, each of these will become clickable, right? So I'm just going to enable the pages as we go along. Okay. So let's go ahead and click on the page for week 1, part 1, so you can kind of see what you can expect from these pages here. Okay. Okay. So under each of these pages here, you will see that there's going to be a small description in terms of what we're going to go over that week. We have the learning objectives for the week as well. Okay. We have the lecture recording, right? So once the lecture is done, I'm going to post it, upload it to YouTube. I will have the link for that here. And so if you want to access the lecture recording, you can click on that here, right? All the assignments that are due that week, you will have access to here as well. So you can see that there is a link to the introduction assignment, a link to homework 1, as well as all of the relevant files that you're going to need for that week as well. So all the lecture notes, any homework solutions that I post, any exam solution, any study guides or handouts, they'll all be here on these daily pages. Okay. So definitely check these out. I'll try to have these up, the night before the lecture, right? So I'll have the page for week 1, part 2 up by this evening, so that you can take a look at it before the lecture tomorrow. I would definitely take a look just to get a sense of what you can expect, and download any of the lecture notes that you need. Okay. But these pages will be constantly updated, so just make sure you're checking these out. Okay. Okay, so that's the home page. So definitely check out the outline when it's relevant. Okay. Next tab right here is the assignments tab, right? So if you click on assignments, these are all the assignments that you are going to be expected to know. Okay. So like I mentioned, there's going to be 5 homeworks, so not including the introduction. So there's homework 1 due at the end of this week, homework 2 due next week, 3, 4, and then 5. Okay. So definitely check this page. One thing you'll note on the assignments page is that there is a due date. Okay. Probably if you used Canvas before, you're probably aware of this, right? But there is a day that the homework is due, and there's a day that the homework is available until. Okay. So there's a gap between these, and so don't confuse this date for the due date, right? So the available till, this is basically the deadline to submit the homework late. Okay. So the homework is due on the 29th. But you can submit it at a penalty for 10% each day up until May 31st. Okay. All right. Next tab here is the grades portion. So this is this is kind of a breakdown of your grades here. Okay. So all the graded assignments will be here, and this will kind of give you a breakdown in terms of what grade that you currently have in the course, right? Remember that your current grade at the moment, don't read too much into it, just because I am probably going to scale things at the end of the session. Fluid mechanics is just kind of that kind of class, right? But this will kind of tell you kind of where you stand. Okay. I think I forgot to mention too. So I am going to drop the lowest homework. So the lowest homework is going to be dropped, and so if you do have to miss one, you do have one homework assignment grace. But like I said, this session is going to go fast, and so just make sure that you're on top of all the homeworks. Okay. All right, next link here is people. So this is everyone that's in the class, and so you can kind of see here. Okay. Next tab here is the files tab, and so these are all the files for the class, and so all the homework assignments, all the lecture notes, any solutions that I post, the syllabus is here as well. Now, all of these files will be accessible through the homepage on the course outline, but if you're looking for a very specific file, you can kind of find it in this file tab. Okay. And the last tab here is SOQs, and so I don't think this is active just yet. Generally you have to watch the movie before you have to write a review on it. So don't give me 1 star until the end of the session. But I think that should probably be available at probably by the last week of the session. Okay. Okay. All right. Any questions on the Canvas site? Okay. All right, so like I mentioned, I do try to keep things simple with the course website. I don't do too much here. This is kind of just the bare basics in terms of what you need. I try to keep it clean. But I am updating this site pretty regularly, at the very least with the lecture recordings and with these daily things. Okay. Okay, all right. So we've reached kind of a good stopping point here. It is a little bit early, but I do actually need a drink of water. So let's take a 10-minute break. I'll come back at about 3:55. And so if you want to kind of go to the bathroom or get some water, now's a good time to do so. Okay. I'll sit around here for 5 minutes if you do have a question you want to come up for, but yeah, we'll come back 3:55. Okay. Hi. No, I don't think it. I'll get it. So,
I have a DSS services.
okay.
I submitted it, but, how do you wanna work that? Would you want me to take it like an hour earlier with you?
Let's have you take an hour.
It's just easier if I can like ask a question instead of like that office.
Yeah. Go ahead and schedule for an hour early, because then we're gonna have the second half of the midterm. Second half of the class, I'm gonna have to go back to. Yeah, so can you take it early? That way you can come back here.
Okay, so that 1:30 that you have open?
Yeah.
Okay, fine.
Yeah.
Alright.
Or however much time you need, just schedule it that much time.
Okay.
But yeah, try to end it by, try to make sure your exam time ends by 4:30.
Well, you said it's gonna take all the time. It's gonna take that.
Well, the midterm's it's not gonna be 3 hours.
Yeah.
So it's, I plan it for about 80 minutes for the exam.
Okay.
The homework due this Friday,
Yes, homework 1 to do this Friday. Yeah.
so will that be through all of it? Like, the lectures from all 3 days?
Yep. Yeah, you're gonna need all 3 of the lectures this week. But after today, you should be able to do like the first part of the homework, and then after tomorrow, the next part, and then after Thursday, that.
You get the additional problem.
No. So the additional problems are just there for your reference, and so you only have to do problems 1 through 5. Yeah, it's a good point. I'll mention that after the break. All right, I guess.
I went to F1. The K1. The K1.
I thought you were talking about the rental rate. That happened.
There's one this Friday, right?
No, it happened this Friday. The rental rate. Or,
Yeah, but there is another. There's a mod. I'm not talking about mod.
no, you're thinking about this one. No, in London, there was a rate.
Oh, yeah, that one.
Yeah. It's like, it's the right rental.
Yeah, but it's not all the only, yeah.
It's not like an official thing, it's like credit.
There's an official rate there, is that the same one?
No, you're thinking of the other grad freedom.
Oh, yeah.
That happened like towards the end of last spring. Yeah. They were giving out free tickets for that thing.
I should have tried, I can get some cards for like.
I mean, I took one with her own brother. But. Pushing both around, they're great time. How do you even do it? They're turning 5 and 8. Yeah. They're big, they're tall. They're turning. They can laugh, but they can do it. You don't have to be 15 minutes.
15 minutes for any. Good to nothing, wait a minute.
Universal.
No, what's the universal is
I'll get the book. Universal testing. Nothing to do with no. This morning. Right? You might have. Here's the apartment and then there you go. There's speed in the building. It's more something. That's not reading it, but a lot of passes. No? Get up. There's animals looking after it, helping a lot. But we can't make this one. That's discrimination.
They're allowed to ask, is it required to?
And what services it comes from.
What are you saying, what did you say? That makes so much sense though, because my mom thinks about it really are like crazy. Yeah. It's a big dog and has a lot of changes to baby. And then you don't take it. And we're starting to
All right, it's 55. Now it's 55. Okay, so let's go ahead and get back to it. Okay, so for the first hour today, we've kind of just introduced the course. So we used lecture slides, but I will say that the lecture slides is typically what I don't like to use them, just because I like to kind of write out my thoughts. So you can see I brought an iPad. It wasn't just here for show, but you'll see that we're going to switch to that. But just I use the slides on the first lecture just because I have pictures to show. It helps talk about the syllabus and the course website as well. So let me go ahead and switch over to the iPad. I'm just stalling a little bit, so I know people are coming back. Okay. Try and make it full screen. There we go. Okay, there we go. Okay, so this is kind of how I typically like to lecture here. So I have have my iPad here. Okay, I'll figure out the perspective thing next time, just so it's it kind of flows the whole screen a bit better. For some reason, Zoom wasn't installed on this computer when I came here today, but I'll install it next time, just so we're not in this weird kind of browser thing. Okay. Okay, all right, so let's go and get started. So, like I mentioned, this is kind of what I typically like to do. So let's go ahead and jump right into it. Okay, so first, until the end of class today, we'll see kind of where we are. If we have a bit of time, we can start fluid status just to kind of help you with your homework. But at the very least, I do want to finish these slide collection notes on what I call introduction to fluids. Okay. Now, this is going to be a little bit awkward just because we've already kind of introduced fluids in the class so far. But like I said, normally when I'm teaching this class in a regular semester, this would be the start of day two. So usually day one just kind of getting to know you and stuff like that. Day two is kind of when we kind of start doing stuff. It's just for the summer session, we have both lectures kind of smushed together in one. That's why we're going to repeat some concepts. We're going to talk about density and viscosity again, but those are important. So it's good that we're talking about them more. Okay. All right. So let's start with the exact definition for a fluid. And let me just check the delay here. Okay, that's not bad. Okay. So like we talked about maybe like 45 minutes ago, a fluid is a substance that continuously deforms when under an applied stress. Okay. All right, and of course, the operative word here is continuously deforms, which more casually we say that this is a term for flow. So if you apply a force to a fluid, it's going to move. It's going to flow, right? And it's going to keep doing so as long as that force still remains present, right? So, like I mentioned, the most obvious kind of sense for this is the force of gravity. Right? So gravity is a force that causes a lot of fluid to flow. Right? So if you think of a waterfall, right? So waterfall is a great example of this because, in a waterfall, you have a constant act of gravity that's kind of pulling the fluid down from a higher place to a lower place. Okay. And so because of that, water always flows down the waterfall. And it's constantly doing so because of the effect of gravity. Okay. Right? So you have, a waterfall like this, and you have fluid that's always kind of going over the top of that waterfall. Okay. Okay. So as long as there's a force, fluid's going to flow. There's going to be some motion. Okay. And you can kind of see this on a micro basis as well, right? And so if you think about, right, think about what happens when you squeeze a fluid, right? So let's say that, let's compare two different objects. So let's take a rock versus an object that has a similar size and similar shape. Let's say we have a water balloon. Okay. All right, so what happens when you squeeze a rock, right? So you take a rock, you just find a just random rock outside, you try to squeeze it with your hands, right? Unless you're the Incredible Hulk, probably not much is going to happen to that rock. If you are able to crush the rock, just remind me to never shake your hand because I like all my bones not broken. Right? If you squeeze a rock, nothing happens. Right? Because a rock is a solid, right? So for a solid, right, you can try to apply force, but there's not going to be any motion. Okay. Whereas if you squeeze the water balloon, right, what's going to happen, right? So on the one hand, you may pop the water balloon. That's probably the first thing you may think of. But if you assume that the water balloon, let's say it's not completely filled, or maybe the elastic on the water balloon is really good, right? What happens when you squeeze the water balloon? It's going to change its shape. Right? Exactly. Yep. Exactly. So the liquid in the water balloon is going to flow to the parts where it has the least amount of force being applied to it. Okay. So that's the main difference between a solid and a fluid. So it doesn't take a lot of force to get a fluid going, right? As long as there's kind of a modest amount of force, there's going to be some degree of flow or some degree of deformation within the fluid. Versus a solid, it really takes a lot of force to cause any kind of damage or any kind of motion within that solid. Okay.
It's kind of like the calcium buildup in your system, right? That's when you have a heart attack.
Oh yeah, no, for sure.
They don't extend.
Yeah, no, that's a great point. So yeah, so when you have kind of heart disease, right, you have all these kind of calcium that kind of builds up, all this plaque that builds up in your system, right? It actually makes your blood vessels a lot less flexible, and that's what causes heart attacks and things like that. So great example. So why is that, right? So why, I think intuitively, I think we kind of understand this, but to really kind of understand why this is the case, you really have to kind of look at the molecular level or the particle level of these different substances. Okay. So if you take a solid, right? So let's say you take a metal or you take a plastic and you look at it under like a very powerful microscope, what you're going to see is that the molecules within the solid are very closely packed together, and they often have a very rigid, uniform structure. Right? And so if you look at the molecules, there's going to look probably something like this. Now, of course, if you've taken a material science class, if you've taken solid mechanics, you'll know that there's different degrees of organization. So certain solids like metals have a more kind of uniform, more organized structure. But generally, for every solid, there's going to be a very tight kind of packing of the molecules together. I'm only going to draw 3 rows here. Okay. Right, so that's the first thing you're going to notice in a solid. The molecules are very closely packed. Another thing that you'll notice, or maybe not visually see, is that the bonds or the kind of kind of the forces that are holding the molecules together are also extremely strong. So it's very hard to separate or move the molecules relative to one another. Okay. So that's what gives the solid its structure, right? So not only are the molecules very packed, but they are very strongly bonded to one another. So there's really no movement. So the structure is basically set in a solid. Okay. Versus a fluid. Now there's different degrees of fluids, right? So we can talk about liquids, we can talk about gases. So those actually have different molecular structures. But let's talk about a liquid first. Okay. Okay. Right. Now, a liquid's interesting because the molecules they're still relatively densely packed, right? So you're going to see a lot of molecules together in one place. Okay? But the organization may not be as uniform. Okay, so they may be kind of a bit more randomly kind of assorted. Okay? So there's a bit more randomness in terms of how the molecules of a liquid are organized. Okay, and that randomness is not just for aesthetic purposes. That also means that the molecules themselves are not bonded as close together. So there's a lot the molecules can much more easily kind of slide past each other or separate, which causes the liquid to have its movement. Right. So that's kind of the big difference in between the two. Okay. So that intermolecular movement, interparticle movement, that's kind of what it makes a liquid or a fluid unique compared to a solid. Okay. But like I mentioned, there's not only liquids, there's also gases as well. Okay, so a gas also counts as a fluid. Now, for our purposes in this class, we're going to treat liquids and gases basically the same. They do have their differences, obviously, but in terms of their behavior, especially when you're talking about low speed flow, liquids and gases essentially they behave the same. They just have different density and different viscosity. Okay, but on a molecular level, gas particles are much more kind of loosely dispersed. Okay, so you're going to have your particles here that are much kind of further apart from each other. Okay. All right, and so because the gas particles are far apart, you kind of have the exact same property in fluids where there's very weak intermolecular bonds, if there's even any at all. Okay, so the same kind of property here is also applicable for gases as well. Okay. All right, so those are your three states of matter and kind of a little bit of background. Of course, this is just a very quick introduction, but a little bit of reasoning in terms of why you expect or why you observe different types of behavior for those different states of matter. Okay?
So liquid oxygen, why is it?
Liquid oxygen.
Yeah.
So anything that's in a liquid state would be liquid like this. So the particles would then be packed pretty close together.
That's what space that is floating on.
Yeah, no, that's all that stuff is really so that you have to kind of cool it down quite a bit. Yeah. Now, like I mentioned, so for this class, we'll be talking about liquids and gases, but we're going to have kind of seen them I'm going to kind of use them kind of interchange. Okay. Now, the two most common liquids and gases that we'll be talking about in this class, the most common liquid is water, just because it's the one you see the most, and the most common gas is actually air. So air, if you've ever read a science text before, air is predominantly nitrogen. There's some oxygen, there's some carbon dioxide in there as well. But since air is so prevalent, air actually has its own density and stuff. Okay, now I bring this up just to kind of give some justification for the behavior that we'll see. But in general, we're not going to be looking at individual particles of fluids or liquids or gases. There is a branch of fluid mechanics that does look at particles. It is a fairly big a fairly big field, so that's called Lagrangian fluid mechanics. That's not what we're going to talk about in this class, just because it's not a very good introductory topic. So for most of this class, we're going to be looking at, we're going to be assuming we're going to be taking what's called the continuum assumption. Now, under the continuum assumption, we're going to look at a body of fluid kind of as a whole and kind of describe its motion and describe its forces as a whole. Now, the reason for that is, it does make the analysis a little bit easier, especially when you're learning fluids for the first time. It also makes it kind of a little bit more relatable to kind of how you've learned mechanics, how you learned solids kind of up until this point. Because the way we treat solids is very much in the same way as well. So most of the times when you talk about solid mechanics, you're not looking at individual particles of the solids, you're looking at an entire structure, an entire body as a whole, right? So we're kind of looking at the same for fluids. Okay. Okay. All right. Any questions on this as well, or yet? Okay. Okay. So one last thing I will mention before we move on to dimensions. Like I said, liquids and gases for the most part we'll consider mostly the same in this class, but they do behave differently. So to kind of put it in very kind of simple terms, a liquid is a fluid, and so it continuously deforms if you apply a force. And a liquid will, but a liquid will assume is going to maintain a constant volume.
So without heat, cold,
So we're assuming the temperature is constant. Yes.
because your brakes get a little heat up.
Exactly. Mhm. Okay. So you can squeeze a liquid. You can kind of pull apart a liquid, and it will change shape, right? So there's it's like we said, a fluid will kind of deform and kind of change to whatever shape container that you have, but a liquid will always maintain the same volume. Okay. Whereas a gas we're going to assume is going to fill whatever volume or whatever space of the container that it is contained. Okay. And so that's kind of how we understand kind of liquids and gases in general as well. Okay. A little bit random put this here. I should have put it above when we were talking about molecules, but I just wanted to make sure I mentioned that before we move on. Okay. All right. So now that we kind of have a stronger idea of what fluids are, let's talk about the next point, which is dimensions and units. So a little bit of a detour. But it's worth kind of reviewing this. It's worth going over this just because I think one of the things that makes fluids more difficult, I think, than other subjects is that there's so many different terms and so many different properties that I think you've kind of been introduced to for the first time. It's important to kind of always kind of keep track in terms of what dimensions all the variables that we're looking at are. Okay, so let's define these. Right, so I'm sure you've heard the term dimensions before in your other classes, but to define here as well, dimensions are the physical measures by which variables are expressed. So every variable that we're going to encounter in fluids, every variable that we're going to encounter in this class is going to have some dimensions to it, or actually some won't, right? And we'll discuss kind of those cases as well. Okay? So some common dimensions that you've probably seen, things like mass, things like length, things like time. Okay? Sometimes force, okay? Just because it is convenient to express things in terms of force. Okay? So for example, right, so if we take a very common quantity that we're going to look at in fluids, which is the fluid velocity. Right? Velocity is a concept I think you've seen before, probably in your dynamics class, right? So velocity has dimensions of length over time. Because that's how velocity is defined. So velocity is essentially speed, and speed tells you how much distance that you're going to travel over a period of time, right? If you're driving your car down the 91 at 60 miles per hour, you maintain that speed for an hour, you're going to drive 60 miles in that time. Okay. Right, so oftentimes, in fluids, we use kind of shorthand dimensions here. So instead of writing out length over time, we say this has dimensions of L over T. Okay. And we put square brackets around those points. Okay. All right, and so that's dimensions. Let's define units. So the units are simply just the names under different conventions that we assign to the dimensions. So units are probably what you're more familiar with from previous classes, right? Right. And usually when you talk about units, you name kind of the convention under which you're defining that system, right? So the most common unit system that we use, the one that we like to use in engineering, is the SI units. Right, so the SI unit for velocity is meters per second, right? Or m over s. Right, so there's also the English units, there's the imperial unit systems, but most of the time, we're going to use SI. And for this class as well, I think for the majority of the class, we'll use SI. Now you have to be careful because sometimes you have to convert between different unit systems, and so just kind of be aware of that. Okay. It doesn't happen often, but you'll be surprised. Some when you get out there in industry in the real life, everyone kind of uses the unit system that they like. And if your job is to kind of coordinate between different vendors or different kind of different companies, one company or one vendor may use English units, the other may use SI units. Even between two different vendors that use SI units, one may use meters, another may use centimeters, one may use millimeters, and so you want to really keep track of the units because it's one thing where it's a very simple mistake, but it can lead to very catastrophic mistakes. I think in the programming of one of the satellites recently, they made a simple unit conversion error and led to a $5 million satellite just being bricked, just a piece of space junk, just immediately. Okay. All right, so let's go over some common units and some for some common quantities that we'll see in fluids. Now, I'm not going to go over everything here. There's a full table in the lecture notes, but I will give you some important ones here. Okay, so let's go over. Let's talk about velocity first. We just mentioned it, but might as well just keep it here for completeness. Okay, right. All right. So the dimensions for velocity, like we mentioned, is length over time. Okay. And the SI unit for velocity is meters per second. Okay. Another one we'll see often here is acceleration. So acceleration has units of length over time squared. Okay. Another way that you'll see dimensions kind of expressed here is you might see negative exponents. Okay. So if you have a dimension in the denominator, you may just see people express them as fractions, like I did with velocity. But oftentimes, some people just don't like to put a division sign in a line, and so you'll see certain quantities raised to a negative exponent. Okay. So you can see that this dimension here is length times t to the minus 2 power. That's the same thing as length over time squared. So I'll put both versions there just so you can see, but sometimes you'll see the negative exponents to express that. Okay. And of course, the SI unit for acceleration is meters per second squared. Okay. Another common quantity that you will see that we've already talked about in our introductory slides is the density. Okay. So density has units of mass over volume. Okay. And volume is just length cubed. So the dimensions for density is mass times length to the minus 3 power. Okay. And the SI unit for density is kilograms per meter cubed. Okay. Next one we'll go over is force. Okay. Now, force is an interesting one because force you can imagine, is very common, right? So force is the driving force for any motion, right? So Newton discovered that. But in terms of dimensions, it doesn't fit very nicely into it. Okay? So force equals mass times acceleration. And so if you were to just do that in terms of units, it would look something like this. So you have mass times the length times t to the minus 2. Okay, so that's really mass times the acceleration. Now, I bring up force because, what you'll see often sometimes is that, for certain quantities that are, very, very common, it's a little bit cumbersome to say kilograms times meters divided by seconds squared, right? So nobody says that when they talk about forces. So the SI unit for force, as you probably know, is the Newton. Right? So it's an SI unit that doesn't necessarily match its dimension. It's just more convenient just because we talk about forces so much. Okay. So you want to be aware of those situations where you have a quantity that has a unit that doesn't necessarily match its dimension. And so the first three that we went over, the unit and the dimension, very closely aligned. So they're very straightforward. But for something like force, you have something. Okay. All right. Another one that we'll talk about, especially coming up, especially when we talk about fluid statics, is pressure. Now, pressure is defined as a force divided by an area, and area is length squared. Okay, so we're going to take our dimension for force and then divide it by L squared. Okay? And so if we do that, we get M times L to the minus 1 times T minus 2. Right. So for pressure is interesting because it actually has a couple SI units. And so I would say the most common one that you'll see is that pressure is usually measured in a unit called Pascal. Okay. Right, PA. And you'll see why it's named after him, once we get to the fluid statics. It's not Pedro Pascal, it's a much older Pascal. But Pascal, if you actually work it out in the formulas, Pascal is nothing more than a Newton per meter squared. But for our purposes, most of the time when we talk about pressure, we're gonna talk about it in terms of pascals. Okay. Okay. Good. All right. So there's a lot more that we can go over, but I want to end this just with viscosity. Okay. Okay. So for 6 here, let's talk about dynamic viscosity. So dynamic viscosity has units of mass over length time. Okay. And the units for dynamic viscosity is like we mentioned in the intro slides, is Pascal seconds. Right? So Pascal dot seconds. Which again looks very strange. It doesn't look anything like its dimensions. But if you actually work it out in terms of the dimensions of pressure times time, you can see that it works out exactly. The dimensions are consistent. Okay. And so if you compare these two, right, dimensions for pressure and dimensions for viscosity, right, they're only different by dimension of time, right? So you basically just take pressure, you multiply by time, that gives you units of dynamic viscosity. Okay. Hence, that's why the SI units for viscosity is Pascal seconds. Okay. All right, and so the last one that we'll go over here in this table, just because it's getting a little bit old, is kinematic viscosity. Okay? So kinematic viscosity has much simpler units. It's length squared over time. So length squared time length. Okay? And thankfully, the SI unit for kinematic viscosity makes total sense. It's just meter square divided by seconds. Okay, good. All right, so why are we going over this, right? So on the one hand, this might be interesting just from a trivia point of view in terms of if you ever go to trivia night and they ask you what's the dimensions for dynamic viscosity, it's right here, right? But these are concepts that you've probably seen before. Okay, but the reason we're bringing it up here is that the thing about fluid mechanics is that there's a lot of formulas that we're going to learn, And they're not necessarily formulas that you kind of memorize and kind of plug and chug, just because a lot of formulas that we'll go over are kind of very specific to certain situations. Okay. One thing to always remember that when you have an equation that involves multiple different quantities and multiple different variables, all the dimensions for every term in the equation has to be consistent with each other. Otherwise, the equation would not be valid at all. Okay. So what does it mean to be dimensionally consistent? So if you ever look at separate terms in an equation, you're adding or subtracting them, they must have the same dimensions. Okay. Multiplying and dividing are a bit different. In fact, oftentimes you need to multiply and divide different quantities in order to make things dimensionally consistent. But adding things together, they have to have the same dimensions. Okay, and of course, this is not just true in fluid mechanics. This is true in basically all science, right? So you have an equation. Every term must be dimensionally consistent. Okay? So let's start with a simple example. And by the way, this is problem 2 on your homework, and so just to kind of let you know, or not, it's not exactly this, but they're problems like this. Okay, so let's look at the velocity of a rigid body. So this is probably an equation you'll learn in your first physics course here. Okay? So the velocity of rigid body is equal to the initial velocity plus the acceleration multiplied by the time. Right? So probably you've seen this formula before. Right? So v is equal to v naught plus a times t. Right? Where this v is the current velocity. Okay? V naught is the initial velocity. This a here is acceleration. And t, of course, is time. Okay. Okay. So in order for this equation to be dimensionally consistent, every single one of these terms here have to have the same dimensions, right? So we call this term 1, v naught here is term 2, and the product of acceleration times time, that there is term 3. Okay? So when I say term in an equation, that means just any combination of different variables that are separated by an add or subtract sign. Okay, so let's check the dimensions of each of these terms here and just make sure they have all the same dimensions, which in this case, they should all have dimensions of velocity. Okay, so term one is just velocity. And so velocity has dimensions of velocity. Right? So that's good, right? And so velocity is velocity. Term number two. Term number 2 is initial velocity. Initial velocity is still a velocity, right? So v naught has dimensions of length times the minus 1. Okay, and then we come to the last term, which is not strictly a velocity, but you'll see that it does have the same dimensions. Acceleration times time. Okay, so acceleration, we know from the table above, acceleration has units of length times time to the -2 power. Okay, and time has dimensions of time. Okay, and so we take the product of these two. We're also taking the products of their dimensions as well. Okay. So we take length divided by time squared times time. The time is going to cancel out, and then we're just going to get length over time, which is velocity. Okay. So we perform kind of the stoichiometric conversion here, right? So we have length over time squared times time. This time is going to cancel out with the one of the times in the denominator, and we have just length over time. Okay. Which is exactly the same as all the other units. And so we can say that this equation here is indeed dimensionally consistent. Okay, good. All right, any questions on this this example here? Okay. All right, so let's do one that's a bit more complicated, one that's a bit more consistent with what you're going to see on the homework. Okay, so let's look at an equation here. This is actually taken from the very end of the class, and so we'll see this kind of near the end when we talk about drag and lift. But let's talk about the drag force on a spherical particle flowing in a stagnant fluid. So actually, the video that we kind of saw in the introductory slides, where someone was dropping a marble into those different graduated cylinders, this is an equation that models that behavior. Okay, so we have three terms here, but three terms here are a bit more complicated. Okay, so we have mass times gravity minus pi over 8 times the drag coefficient CD times density rho times v squared, the velocity, times d squared, diameter of particle, is equal to mass times dv dt. Now, I bring this equation up not because we're going to apply it right now, or we're not even going to discuss kind of how we got to this equation. We'll cover that kind of near the end of the session when we talk about drag. But something like this is good because you're going to see equations like this. You can see that this equation is applied in a very kind of niche, very specific scenario, right? You have to have a spherical object, and it has to be settling in a stagnant fluid, right? So fluid mechanics is full of situations like this. You have very specific situations and an equation that kind of governs that very specific situation. Okay. So it's always good to check, just for your own sanity and just to make sure that it's consistent. And also, it just helps you kind of understand every single term in the expression. Just check the dimensions of every single term, make sure they're all consistent, and you'll kind of understand a bit more about the equation. Okay. Okay. All right, but there's a few other reasons I kind of bring up this equation here as well, because they kind of highlight some important themes that you'll see in fluids as well. Okay. All right. So first, let's discuss each of the individual terms. I know I mentioned them kind of briefly, but let's talk about each of them and let's define each of them. Okay, so m is pretty simple. M is just the mass of the particle, okay, or the object. G here is gravity, right? So those are kind of, those are pretty consistent. Those are, you've seen those before. Okay. All right, so it's the second term here that's the most complicated. Let's talk about CD first. Okay? So CD is what we call a drag coefficient. Okay, so what the drag coefficient is not really important at this point. The important thing here is the fact that we're utilizing what's called a coefficient. Right, so this is something that's very, very common in fluid mechanics, and it takes several forms. And so whenever you see something that is a coefficient or a number, what that tells you is that that quantity is a dimensionless quantity. Which may seem very counterintuitive, right? So we had just finished, we wrote that kind of big table and said that all of these different variables, all these different quantities have dimensions. And so what do you mean that we have certain quantities here that don't have dimensions, right? What does that even mean? So usually whenever you have a coefficient or whenever you have a dimensionless number, usually those represent ratios of some kind. Okay? They're the ratio of some force divided by another force. Okay. All right. So in terms of the drag coefficient is a ratio of different forces. So it's a ratio of the force kind of on the front end of the object and the back end of the object as well. Okay, so since you're taking a force divided by a force, you end up with something that's dimensionless. Okay. Another common number that we'll see throughout fluid mechanics is something called the Reynolds number. And so the Reynolds number is a ratio of the inertial forces in a flowing fluid divided by its viscous forces, right? So again, it's a force over force, and so you end up with something that's dimensionless. Okay? Now, just because something is dimensionless doesn't mean it's meaningless, right? So ratios can often be very insightful for these as well. Okay. But I do want to kind of bring that up just because that is a constant theme that you'll see in fluids as well. Okay. So this P symbol right here, remember this is density. Okay. Remember density has a symbol rho. Okay. V here is velocity. Okay. And then D here is diameter. Okay. All right, so all those are kind of a bit more straightforward. Okay, good. So another reason I bring this equation up here is because of the last term as well, right? So you can see we have a derivative thing, right? Now, we're not really going to be solving differential equations in this class. We will for a little bit when we go over Navier-Stokes, but just those are going to be very simple differential equations. But you are going to see derivatives a lot in these kinds of expressions. Okay? So what is the dimension of a derivative quantity? So the dimensions of a derivative quantity is you literally just take the whatever dimensions are on the numerator divided by the dimensions on the denominator. Okay. And so in this case, in our numerator here, we have velocity. Okay. And since we're taking the derivative with respect to time, we're going to take the dimensions of velocity and divide it by time. Okay. And so the dimensions for velocity, remember, is length over time. Okay. And then dimensions for time is time, right? And so we divide by time, we get length over time squared, which is the same as acceleration. All right, so don't be intimidated by derivatives, right? So it's very straightforward to get the dimensions. You just take the numerator divided by denominator for the dimensions. Okay, good. All right, so we've identified every single term or every single variable in this expression, but just like the previous example, every term here should be dimensionally consistent with one another. Okay, right. So if we compute the overall dimensions for term 1, term 2, term 3, they should all be the same. Okay. Yeah. 8. Yeah. Yeah. So pi over 8. Yeah, that's meant to that's because it's a sphere, and so that there's a factor that comes from the volume or surface area. Okay, so let's do this very quickly, just because I do want to kind of move on. But let's look at the dimensions of that second term there. I think that's the one that's a bit more confusing. Because we can kind of hopefully you can already tell that the first term there, the mass times gravity. Gravity has dimensions of acceleration because g represents the acceleration due to gravity. So first term and last term are the same. In fact, they have dimensions of force, right? They have a mass times an acceleration. The only thing that's meant to be determined here is whether that middle term, that pi over 8 times the drag coefficient times the density, velocity squared, diameter squared, whether that also has dimensions of force as well. Okay, so let's check that. Let's check that out. Okay. All right, so let's write out each of the terms here, and we'll write out their dimensions, and then just like before, we'll perform the stoichiometry and then get the overall dimensions for this term. And I'm kind of intentionally writing them kind of further apart just so we can write their dimensions into that expression. Okay. All right, so let's start from the left and then work our way to the right. So first we have pi over 8. Pi over 8 is just a number. So every single number, pi, any kind of factor, 1/2, 1/3, those are dimensions. Okay. So this has no dimensions because it's just pi over 8. Okay, next we have the drag coefficient. Just like we said before, drag coefficient, it's a coefficient, it's a ratio. So that means the drag coefficient also is dimensionless. So there's no dimensions for the drag coefficient. All right, next we have density. Density we've seen before. We just look back up in our table. Density has dimensions of mass over volume. So that's mass over length cubed. Okay. All right, next we have the dimensions of velocity squared. So we know the dimensions of velocity. Dimensions of velocity is length over time, but we are squaring the entire quantity. So that means we're going to apply that square to every single quantity within the dimensions for velocity. Okay. So the dimensions for velocity squared is actually going to be length squared. I can write a normal looking 2 over time squared. Okay. And then finally, we have dimensions of diameter squared. Diameter is a length. And so the dimensions for diameter squared is just length squared. Okay. Okay. All right. So let's go ahead and multiply all these out, and then let's check the dimensions for this term overall. Okay. Okay. So on the numerator here, we have a length squared from the velocity squared, a length squared from the diameter squared. That's length to the 4th, right? And so that's going to cancel out with the L cubed on the bottom. Okay. And so it's going to leave us with just one length up top, right? There's nothing to cancel out the mass. There's nothing to cancel out the time. And so the dimensions for this term overall are mass times length divided by time squared. Which, if you refer this back to our table for dimensions, you'll see that this is the dimensions of force. Okay. which of course is consistent with all the other terms in our equation. So this expression here, dimensionally consistent. Everything has dimensions of force as it should be. All right. Any questions on this example here? Okay, good. All right, so that's dimensions, and so maybe a little bit boring, but it's important. Next thing, let's go over the fluid properties as well. So we're going to talk about density and viscosity again, but also a couple other properties as well. Okay, so remember kind of what we mentioned in the beginning slide, that when you talk about the properties of a fluid, oftentimes you're talking about intensive properties. Okay. And what that means is that, no matter how much amount or how much, volume of fluid that you have, the intensive properties are consistent because it's a property that's intrinsic to the fluid material itself. All right, so let's talk about some common fluid properties, and let's kind of define what they are and kind of what they represent for a fluid. Okay. All right, so first one, we've already talked about it. Let's talk about it again. Let's talk about density. Right. So density, remember, density characterizes how much weight or how much mass a fluid will have per volume within the fluid. So fluids that are more dense will have, will be heavier or have more mass per unit volume. Okay. And density, I think we've all kind of seen that definition for density. But density is a measure of just how much or how dense or how heavy the molecules that comprise the fluid are. So fluids that are comprised of molecules or comprised of atoms that are more just have more mass, just have more protons and more electrons, more neutrons than other fluids are going to have a higher density. Okay? So the very classical high density fluid is liquid mercury, right? So mercury, you know where it is on the periodic table. It's way down there. So mercury is very dense compared to water, where water just is comprised of hydrogen and oxygen. Right. Density, it also kind of measures how tightly the particles are packed together, right? So a fluid that has a higher density will often have particles that are packed closer together as well. So the intermolecular distance between particles is much less in high density fluids. Right, so the definition of density is equal to, right? Remember the symbol that we give density is rho, right? I know with my writing it's a little bit difficult to tell, but for density I try to make the straight part of the P kind of have that little bit of a forward tilt. So density, just you take whatever mass of substance that you have, you divide by the amount of substance that you have in terms of volume. That gives you density. Okay. All right. So I bring up kind of the molecular kind of microscopic kind of origins of density, just to kind of illustrate to you that density does change. Right? So you can actually alter the density of a fluid. And it's not that it can change just on a whim, right? So water just doesn't wake up one day and say, I just thought I'm going to be less dense today. It depends on certain other external factors. And so the two most common ways for density to change in a fluid is due to temperature and due to pressure. So the way every fluid reacts to changes in pressure and changes in temperature, it depends on the fluid. There are mechanistic reasons for that. So there you can look at the molecular level and kind of see exactly how those intermolecular forces change. That's usually not that useful to know just because every fluid is so different, but it is useful to kind of know kind of the general trends. Okay. So in general, right, as temperature goes up, so as you increase the temperature of a fluid, generally its density will go down. Right? The reason for that is as you increase the temperature, you're increasing the amount of energy that all the individual particles have, because temperature is essentially just a metric for energy. Okay. So as the amount of energy goes up, that kind of gives the particles more energy to kind of break its intermolecular bonds. Hence, it kind of spreads out a bit more. Okay? So density will tend to go down with increasing temperature. Okay. Whereas for pressure, the trend is the opposite. So as you increase pressure, right? So as you increase the pressure on a fluid, its density will go up. Okay? The reason for that is, you increase the pressure, that kind of, you literally kind of forcefully kind of squish or kind of push the particles kind of closer together, and that will cause them to be more dense. Okay? So you have more particles occupying the same amount of space. Okay. Okay, so it's important to kind of know those trends. Okay, but with that said, for our purposes in this class, most of the time we're going to ignore these changes. Okay? Maybe I shouldn't say for most cases. I should say most cases in this class we can ignore changes in density. But a lot of really interesting engineering applications have to deal with exactly that fact. The fact that as you heat up a fluid, as you increase its pressure, it does change. But for most, especially when you're first learning fluids, we assume the density is constant because things do get a bit complicated when densities change. Okay. And so this leads to actually a very important assumption that we're going to make a lot for this class, which is the assumption of incompressibility. Okay. So incompressibility has a more precise definition. We'll kind of define that once we kind of cross that bridge for this class. But for most practical purposes, in terms of the equations that you're going to use, in terms of the derivations that we're going to use, the theory that we're going to go over, whenever I mention that a fluid is incompressible, it basically means that its density is constant. Okay. Okay. All right. So just for fun, let's talk about the densities of certain fluids, certain common fluids. I'm not giving this to you to memorize, right? So I'm not going to ask you for the density of blood just on a hat. But this is just kind of give you a sense of numbers in terms of which fluids are more dense than others and how much more dense that they are than others. Okay, so let's start with water. That's our most common fluid. Okay. So the density of water, and you'll see that it's a very convenient number. This is one that you probably will memorize. Okay. So the density of water is approximately 999 kilograms per meter cubed. You're probably thinking, why is it not just 1,000? Well, it does depend on the temperature. Okay? But in order to get that density up to 1,000, you do have to cool the water down actually quite a bit. Okay, so specifically, this is the density of water at 60 degrees Celsius. So decently warm, but so that is a bit warmer than room temperature. But density of water is close to 1,000 kilograms per meter. Okay. In fact, because water is so common, when ancient people back in the SI nation, I don't know, when they were defining the unit system, they used water as a reference, right? So that's why the density of water is close to 1,000. Okay, next let's talk about the density of air. So we know air is a gas, right? And so in general, gas is going to be a lot less dense than water. Okay, but how much less dense is it? So the density of air is actually 1.225 kilograms per meter cubed. Okay. And this is at about 25 degrees Celsius. Okay, so that's about room temperature. Okay. So you can see that air is a lot less dense than water, much less dense than water, right? So it's about 1,000 times less. Okay, right. So if you ever go to a swimming pool, you go underwater, you blow air bubbles, you know that those bubbles rise rapidly to the surface because air is just way less dense than. All right, just for fun, let's talk about the density of blood, okay? Right, so they always say blood is thicker than water, but you know, has anyone ever asked the question, is blood denser than water? Well, it is. So blood actually has a density of about 1125 kilograms per meter cubed. Okay? And this is at about 60 degrees Celsius. Okay? So blood is in fact denser than water. Okay? We'll answer the other question soon. Right? So we'll see that, you know, we'll answer the question, is blood actually thicker than water? But to do that, we have to talk about its viscosity. Okay? Okay, any questions on this so far? Okay. All right, so a couple more definitions before we jump to viscosity. So let's go over the two other quantities that we talked about in the intro slides. Okay. First, let's talk about specific weight. Okay. So not that common, right? So I would say specific density is used way more than specific weight. Specific weight is just another way to express density, specifically on planet Earth. Okay. So specific weight is defined as the weight of a substance divided by the volume. So we're basically taking the mass and we're multiplying by gravity in order to get weight, right? So that's how you get force from that, right? And so to get specific weight, you're going to take the density and just multiply by gravity. Okay? And remember, the symbol that we get for this is gamma. Okay? So gamma is just density multiplied by gravity. Again, specific weight not used all that often, but we will use it tomorrow once we start talking about fluid statics. Okay. Okay. Specific gravity, another very niche quantity, but you know it is interesting. So specific gravity is just the ratio of the density of whatever substance that you're considering divided by the density of water. All right, and so this has a very specific, very niche purpose, oftentimes just for trivia purposes. And so if your specific gravity is less than 1, okay. So let's say you're considering the specific gravity for, I don't know, plastic, right? So if that's less than 1, then that substance will float in water. Okay. But if a specific gravity is greater than 1, it's going to sink. Right. So specific gravity, you know, again, not I would say very uncommon to see, but it is kind of fun to kind of think about whether something will sink or sink or fall. Okay. Okay. Any questions on this before we move on to viscosity? Yes. Yes. Yeah. Yeah. Just because water is so common, but in theory, you can come up with specific gravities for other fluids as well. You can think of a specific gravity for air or for like liquid mercury, but just because water is so common, that's what it's. Yes.
When you say water, do you mean H2O? I've seen it saying for H2O and water, separate things.
So mostly it's H2O, but you may see a modified specific gravity for like salt water. So if you add like, you know, salinity to the water, like let's say you're designing boats, you know, salt does alter the density of water just because you have the salt that's kind of mixed in. But specific gravity kind of in its pure form is just pure H2O. Any other questions on this? Okay. All right. So let's go ahead and move on to viscosity. Okay. All right. So viscosity is a little bit trickier to define, at least kind of quantitatively, without getting too much into the math. It's also a very new quantity, right? So you probably never have talked about viscosity ever in your previous classes. But let's start with kind of the casual definition. So viscosity kind of describes how sticky or how thick a fluid feels. Okay. Right. So fluids with higher viscosity will just kind of feel stickier. It'll stick to your fingers a bit. Okay. Now, the other way to kind of describe viscosity is that viscosity will describe the resistance to flow. So another way to describe flow is that when a fluid starts to flow, its momentum is changing, right? And so viscosity will tell you, how much the fluid will resist it. Okay. Now that's kind of very interesting way to describe it because there's a certain thing for solid that describes the same thing as well, right? So we know just from our understanding of mechanics and solids that certain objects will be much harder to get moving than others, right? So if you try to push, I don't know, a stapler, right? So I can take the stapler, just yeet it across the room pretty easily, but you can't do the same thing to a car, right? So a car has much more inertia, right? It's much more difficult to change the inertia or the momentum of a car, right? So what's the difference between a stapler and a car, right? So they're different masses, right? So for solid objects, the main quantity or the main variable that describes its inertia is its mass, right? So the more mass an object has, the harder it is to change its momentum. Right? Fluids is the same way. So fluids also has density. So more dense fluids also will be more difficult to get going. But because of the nature of fluids and the way that it flows, we also have viscosity that kind of dictates that. Okay. Okay. So to kind of illustrate this, let's again just go back to, I always go back to honey or molasses because that's kind of the viscous fluid that everyone knows. Okay. Okay. So let's compare the sensation of honey sticking to your finger. So let's say that you stick for some reason you're made of money. You can just buy a huge vat of honey and you want to waste it just by throwing your hand in there. Honey is really expensive. I should cook with that versus a tub of water. Okay. Okay. All right. So this is a great kind of illustration of viscosity, right? So the honey, which is more viscous, will stick to your fingers just because it has higher viscosity, right? But what's really going on here when you kind of look at this phenomenon? Okay. So if you think about it this way, if you think about the fluid that's attached to your finger, technically your finger, if you just kind of hold it stationary, your finger has zero momentum. right? So stationary objects have zero momentum, right? So let's say that you have your finger here, right? Okay. Draw a fingernail just to make it actually look like a finger, right? If you have honey, right? Let's say there's a kind of a thin layer of honey around your finger, right? It'll drip down eventually, right? So it'll fall off your finger if you leave it there and somehow you just have nothing to do for an hour, right? The honey will drip down. It's just going to take a long time, right? Right. So when fluid drips off your finger, the main force that's acting on it is gravity. Okay? Right. Right. So by gravity and just by the nature of fluids is if you apply a force, it's going to flow, right? That force is going to pull the honey off your fingers. But since your fingers have zero momentum, they're stationary. That means that kind of momentum is being taken up by the honey as well. Okay. So it takes a while. It takes a while for gravity to actually have an effect on the honey to cause it to flow. Okay? Versus if you did the same thing with water, right? So you dip your finger in water and you pull it back up, right? The water is going to fall off your fingers much more easily. Okay, just because water is a lot less viscous. It has the same forces, right? So water is still going to have gravity acting on it. In fact, if you compare the densities of honey and water, you'll see that they're actually quite similar. They're pretty much the same. I think honey might be a little bit denser than water. But because of the difference in viscosity, the water is going to flow down much more easily because its momentum can change much more easily. Okay. Any questions on that kind of illustration there? Okay. All right. So let's get into the quantitative definition. Okay. So I think this definition is kind of fun. I think when you're first describing viscosity, this is the way to do it. But it does have a strict kind of definition here. Okay. So quantitatively, viscosity describes the relationship between what's called the shear stress and the strain rate in a fluid. Okay? And so the exact formula is the following. So we have tau is equal to mu, which is our viscosity, times du dy. Okay? Which I know are all symbols except for the viscosity are all mu. But we're going to see that this formula here kind of captures the exact kind of qualitative definition that we talked about. Okay. Okay. All right. So let's define each of the symbols here. Okay. All right. So tau here, this is what's called the shear stress. Okay. So a shear stress is basically akin to a force. Okay. It doesn't have the same units of force. In fact, it has the units of pressure. So it's a force divided by an area. But you can think of it, intuitively as some kind of applied force on the fluid, okay? Mu here is the viscosity. That is the man of the hour. That's who we're discussing, viscosity, okay? And then this derivative, the du dy, this is the strain rate, okay? Specifically, it is the change in velocity. So u there is velocity over a change in distance. So it's velocity over distance. But for our purposes here, strain rate is kind of a surrogate or kind of a stand-in for flow. All right. So what this formula is basically telling us here is that, it tells us the relationship of how much force that we have to apply to cause a certain amount of flow in the fluid. Because this formula always has to be satisfied. Okay. All right. Because let's look at certain situations where we have a fluid with high viscosity versus low viscosity. Okay. Okay, so let's look at a situation where we have low viscosity first. Okay. All right, so no matter if we have high viscosity, low viscosity, that same formula does have to be satisfied. Okay, so we have tau is equal to mu times du dy. Okay. Okay, so in this situation, when the viscosity here is low, right? Right? And that equality we know has to be satisfied. That means if we want a situation where we have let's say, a medium amount of flow, right? In order to cause that medium amount of flow, we don't need that much force, right? So the shear stress here will be relatively low. Okay? Right, so think of your low viscosity fluid. So think of like air, think of water, right? So it doesn't really take a lot to get them going, right? Because the viscosity is low, you can apply just a modest amount of force, and that's going to cause flowing to occur. Okay? Versus, let's look at a situation where we have a high viscosity fluid. Okay? So same formula. Okay? Right, so this formula is valid, again, for all types of fluids. Okay? But if your viscosity is high, okay, and let's say again that we want to cause a medium amount of flow, okay, and then we ask ourselves, how much force is required to cause that medium amount of flow, right? We have the product of something that's high and medium, right? So that means the shear stress or the force that we need is something that's relatively high. Right? So that simple formula there, I will say we're not really getting to the details in terms of what that means. We'll talk about that once we get to Navier-Stokes. But that simple formula there will tell you kind of the relationship between the amount of flow that you get versus the amount of force that you apply for different types of fluids that have different viscosities. All right. Any questions on this? Okay. All right. So before we kind of get to the more, I would say, miscellaneous properties of fluids, let's talk about, let's give some examples. Okay. So again, let's look at the viscosities of water, the viscosity of air, and the viscosity of blood. Okay. So viscosity is another property that does actually change with temperature. It doesn't change as strongly as density. Density has a much stronger dependence on temperature, but for all of these, we can assume that they're at room temperature. Okay? So for water, the density, dynamic viscosity is 8.9 times 10 to the minus 4 Pascal seconds. For air, we generally we expect it to be less viscous than water because air is much easier to get flowing than water. So the viscosity of air is 1.81 times 10 to the minus 5 Pascal second. Okay. Right. So you can see it's about 10 times less viscous, and so it's 10 times easier to get air flowing than water. Okay. Right. And then finally for blood, so we can answer the question, is blood thicker than water? Okay. It's really just kind of a movie phrase, but there we can actually test it scientifically. So the viscosity of blood is 2.87 times 10 to the minus 3 Pascal seconds. Okay. Right. So in fact, because that last exponent there is 10 to the minus 3, the viscosity of blood is actually higher than water. So we can actually say scientifically that blood is actually thicker than water. Or I guess the more scientific definitions is you can say that blood is actually more viscous than water. But I think that doesn't make for a very good movie catchphrase. Okay. Next time your cousin is asking you for money and they tell you that blood is thicker than water, you can say, well, actually, blood is more viscous than water. So therefore, I do not need to lend you $50. My cousin's asking me for money a lot. All right. Any questions on viscosity? Okay. All right. So like I said, density and viscosity, those are the two main properties that's going to reoccur quite a lot, throughout this class. There are other properties for fluids. They're not going to be as relevant for what we're going to do in this class. But, I do want to mention it, especially because we just have 20 minutes left in class today. Okay. We're just going to go rapid fire through a few more properties that, you will see if you look up a property table for fluids, you'll see these. But, they're not going to be too important for what we're going to do. Okay. Okay, so the first one is compressibility. Okay. So compressibility actually is related to density in a way, but specifically it's more about how the fluid, how fluid's volume and density change as the pressure changes. So like we mentioned, before with density, generally as you increase the pressure on a fluid, its density will also increase. Okay. Now the degree in which that changes is governed by its compressibility. Okay. So the property that describes this is something what's called the bulk modulus. Okay. So the bulk modulus, often we give it the symbol EV. Okay. Is equal to change in pressure. Let's do it like this actually. So let's do change in pressure. So that numerator there is change in pressure divided by the relative change in density. So fluids with a lower bulk modulus basically means that it doesn't require that much pressure to occur to cause a change in density. Okay. But again, for our class, remember, we're mostly going to assume that our fluids are incompressible. So incompressible fluids basically have an infinite bulk modulus, right? Now that's impossible, of course. It's impossible for a fluid to have an infinite anything. But for our intents and for our intents and purposes, for our assumptions, we're going to assume the bulk modulus is so high that it's almost impossible to cause a change in density. All right, so the reason we mostly ignore compressibility, most fluids, even gases, right? So even gases at room temperature are basically incompressible. Um, it's only when you get to very niche scenarios, mostly in the aerospace business, right? And so most of the times where compressibility becomes an issue is when you have supersonic flow. So supersonic basically means the fluid is moving at a speed faster than the speed of sound. So you're talking about the design of very specialized, very expensive, fighter jets or airplanes, things like that. And so in those situations, compressibility is very important because then you're going to deal with things like shocks and aftershocks and things like that. But for most, I would say more mundane applications for fluids, things you're going to see just as a human standing on Earth, most fluids are incompressible at this speed and at this temperature. Okay. So compressibility very important for certain areas of engineering, but for us, not really important. We're going to mostly neglect it until the very end of the class. Okay. Now the next property, this is probably one you've seen before, maybe in a high school science class, vapor pressure. Right. So vapor pressure it's a gaseous pressure, but it's very specific. It's the gaseous pressure that exists above a a container of liquid. All right, and so if you have just a container of liquid, so let's say you have kind of a glass of water here. So if you leave just a molecule of liquid or just a container of liquid like this, right? What's going to happen is that there's actually a continuous exchange of particles. So there's going to be some liquid particles that escape and become vapor. Okay. Right. So that just naturally happens. That's just kind of what we call kind of natural evaporation. Okay. But those particles actually don't get that far, and so they actually, unless you're actually heating it up, or unless there's changes in humidity that's around the surface. All right, so a lot of those kind of particles just kind of hang around, just kind of at the very top of the fluid, and eventually, just by gravity, they actually just come right back. Okay. All right. So what's happening basically is that over any kind of container of liquid, there's kind of a constant exchange of particles that occurs, and that constant exchange, or that kind of thin layer, gives you your vapor pressure. Okay. Now, vapor pressure is often talked about within the context of boiling. Okay. So when you talk about boiling, right, boiling is when you heat up a fluid hot enough so that a much of the fluid is being turned into gas.
Like that, reset happening.
That's part of it. Yeah. So the vapor.
The vapor.
Exactly right. So that chemical leak that's happening in Garden Grove. So yeah, that liquid is just kind of out there. So then that liquid's turning into vapor, which is escaping into the atmosphere. Yeah, which is causing people to evacuate their homes. Okay. Right. So boiling is kind of one of those things which, I think we all we have an intuitive kind of understanding of kind of what occurs when boiling happens. You heat up a pot of water and heat it up until it bubbles vigorously. But this is kind of the more strict definition. Okay. Because generally, as you heat up a fluid, as you increase its temperature, its vapor pressure also increases as well. Okay. So boiling is actually a very specific point. So boiling occurs when the vapor pressure of a fluid equals that of the atmospheric pressure around the fluid. The one thing you probably have heard is that, if you were to go into the mountains, water boils at a much lower temperature in the mountains, right? The reason for that is that, as you get higher and higher above sea level, so generally the way people do this is to get onto, go up a mountain, the atmospheric pressure decreases, right? So the reason boiling occurs much faster in the mountains is because, that it takes a lot less energy, it takes a lot less temperature to get the vapor pressure of water up to atmospheric if the atmospheric pressure is, much lower to begin with. Right? So next time you go snowboarding, think of that. So it has nothing to do with the temperature. It has really just to do with the atmospheric pressure. Okay, it's not because the mountains are colder. That's because the water boils faster. It's because the atmospheric pressure there is just much. Okay. Okay. Any questions on vapor pressure? Okay. All right. So last property that we'll talk about before we head out for today is surface tension. All right. So surface tension, is another very fascinating subject. I think it leads to a lot of very interesting phenomena. So if you've ever looked at those water skating bugs, right? So those bugs that can just kind of float on the water, right? They're literally just relying on the surface tension to keep them up. Okay. Okay. So what is surface tension? So whenever you have an interface between a liquid and a gas, there's kind of a thin skin that kind of forms right at that interface. Okay. Now, what's interesting is that that skin can actually support a very small amount of weight. So why is that? Why is that, that thin layer of fluid at the top can support a bit of weight? Well, it has to do with the intermolecular forces. And so, and I promise after today, this is the last we'll talk about molecules and fluids. Okay. Okay. So ideally, for a typical fluid particle, a typical fluid molecule, it likes to be surrounded on all sides by other fluid molecules. Okay? So a typical fluid molecule is something like this, right? It likes to be surrounded on all sides. So it's a very social thing. Right? Right. So let's say, this is a little happy molecule that has friends on all sides. Okay. Now what's happening kind of on the molecular level is that, there's this molecule is applying forces to kind of attract all of its friends to it. Okay. So there's basically kind of an equal and opposite force for every single molecule here. Okay. That's essentially what kind of pulls them together. All right, so that's ideal, right? So if you think about a fluid molecule that's in kind of the interior or below the surface of a fluid or of a liquid, that's what happens, and those fluid molecules are happening, okay? But on the surface, this doesn't happen, right? Because on the surface, a fluid molecule is surrounded by gas. Okay? Okay? So near the surface, you know, a liquid molecule does have some neighbors, right? But it's not going to be surrounded on all sides. Okay? Right? Because above this fluid particle here is gas. Okay. And the thing about gaseous, you know, molecules is that they don't really mix together with liquid molecules. Okay. And so this molecule here is not so happy because he doesn't have as many friends. Okay. There's still forces. Right. So he's still applying forces where he can to attract other molecules, but you can think of it like this, where, you know, the forces that would be applied here, right, on if there were other liquid molecules there, those are being kind of compensated by applying extra forces to the other liquids that are on the surface. Okay? Okay, so these forces just along that thin layer on the surface are kind of extra big to compensate. Okay. So it's you know, you can almost think of it like it's like, you know, this guy only has a few friends, so the friends that he does have, he's kind of holding them even tighter to make sure that they don't leave. Okay? And those extra forces there create that kind of thin skin, which we kind of observe as surface tension. Okay? Now, surface tension is really interesting, just for the, you know, cases that I've mentioned before. But surface tension also is kind of the explains why if you take a droplet of fluid, right? So let's say that you take a droplet of water, it always forms a kind of spherical or sometimes that teardrop shape. So that shape is determined by the surface tension. So without surface tension, you know, if you had a droplet of fluid, it can form in just kind of any shape. But because of the surface tension, it like all the fluid in that droplet kind of pulls on each other, and that's why it kind of forms that spherical shape. Okay. All right, so surface tension, very cool, very interesting. Also, not important for what we're going to do in this class. Okay, so this is kind of the last that you'll probably hear me mention. All right, any final questions on this before we wrap up for today? Okay, all right, so we're out of time for today, so thank you guys for coming. We'll be back here tomorrow, and tomorrow we'll be talking about fluid static. So hope you guys have a good rest of your evening, and I will see you all tomorrow. Four thirty six. Yeah, yeah. So prerequisites are going to be vibration for version 1, and the heat transfer.
Have a good one. I say. This one's the heat transfer, exactly. And heat transfer only in spring.
Yeah, the lab also only.
Yeah, timing is always a bit challenging. Yeah, because right now I'll fill up on this for next fall.
Yeah.
I'm like, I don't know where else to add.
Yeah, it was a little bit awkward this summer because we were trying to offer fluids in session A, transfer session B, one with the lab, so people would catch up. But the heat transfer didn't get enough enrollment, so it was actually, it was a little awkward because we're offering this class, but most people can't even use it because of heat transfer. They could take the heat transfer.
Okay, yeah, because it's all Professor Park teaching the forces of things earlier.
Yeah,
So
yeah.
I was like, oh, maybe I can join you too. So.
Oh, yeah, but probably next year.
No, I was just trying to relate your stuff because I used to work at SpaceX, so
Oh, cool.
yeah, so I'm trying to just relate it all. Use water to pressurize everything. And
Yeah.
just check it before they put the actual fluids into it.
Nice.
So I'm just that's the way I'm starting to learn this stuff. Is I actually did that. I just didn't know why I was doing it.
Yeah.
So,
No, I mean, that's the best way to learn. It's like
Yeah.
you see the applications out there and then you kind of learn the theory
Mhm.
that's behind it. So,
yeah, it's interesting stuff. Okay, now I'm understanding why.
nice. Good.
Thank you, Doctor.
Yep, no problem,
I'll see you
Chris.
tomorrow.
Yep, see you tomorrow.